Algebra 2, Unit 6, Lesson 18 is called Modeling Circular Motion. Our learning goal today is I can use trigonometric functions to model circular motion. The good news is we've already been doing that. We've been doing a couple Ferris wheels and I believe windmills that are going in a circle. So should be somewhat of a review today. All right, so here's our warm-up. Take a minute, pause the video, read the warm-up activity and give it a try on your own. And when you think you got it, go ahead and turn the video back on. I'm going to go ahead and just do it right now. So the y-axis is the vertical position in inches, and the x-axis is time in seconds of a bike wheel, s seconds after the wheel begins to spin. Which bike has larger wheels? Explain how you know. So if you think about a bike wheel too, okay, you got a wheel here like this, and you got your wheel usually rests on the ground. And I'll put the y-axis here. So if you think about it, the highest point is going to be up here, and the lowest point's right there at 0 on your wheel. So it's kind of like this graph A here goes up to like 26 and down to 0. So that would be kind of like your radius is 13. Okay, so to get up to 26, it's like you got a radius of 13 times 2 gives you a diameter of 26. Whereas the other one, if you look at that wheel, it goes up to 20. Okay, 20 to 0 down there. So that wheel would look more like this. Okay. Kind of like this wheel here would be 10, and then another 10 up there. Okay, so obviously graph A or wheel A so basically radius of 13 on wheel A versus radius 10 on wheel B. Okay. Which bike's wheels are spinning faster? Explain how you know. So faster would have to do with the time that it takes to do a full cycle. So if I look at graph B here, a full period is in about 0.3 of a second. So graph B has a period of 0.3 seconds, whereas graph A, we'll take a look at the period length on graph A. Graph A has a period length of about 0.4. So obviously, to do a full cycle, a full period, graph B is definitely quicker. So our answer would be graph B is spinning faster. Okay. I also had some students when we did this in class, they said that graph B completes more full cycles in the same amount of time. So you could also think of it like that too. If you just say, okay, that's 1 period, 2 periods, 3 periods, 3.5 periods basically, versus graph A completes 1, 2, 2.5. So, obviously it's going to spin more times in 1 second, so it's obviously going faster. That would be acceptable as well. Okay. Okay, pause the video, take a minute and read this situation. What we got here is a carousel moving counterclockwise. So Jada begins at position J, Noah at N, and Elena at E. So they mark some angles here. So pi over 2 radians, you should know that that's 90 degrees, and 2 pi over 3 is 120 degrees. If you don't remember, pi over 3 is 60. Should have that memorized. So 2 times pi over 3, I multiply each side by 2, I get 2 pi over 3 would be 120. Or I guess you could multiply by 180 over pi, and your pi's would cancel, and 3 goes into 180 60 times, so then you get 120 degrees either way. But basically what ends up happening is you got 90 here, and then this is 120. Okay. So the radius of the carousel is 20 feet, so I'm going to go ahead and mark that. How far does Jada travel to reach Noah's starting position? So how far? Now, a lot of people want to put pi over 2 radians, which is correct. She does travel pi over 2 radians, but it wants to know how far. So we're going to want to know the actual distance. So in other words, we're looking for the arc length right there from J to N, the measure or the length of arc JN. So we got to do a little bit of geometry here. So you might remember if you take your angle, in geometry, if you take your central angle, divide by 360, and times that by your circumference, that'll give you your arc length. Okay? Now circumference, you hopefully remember, circumference is equal to 2 pi r, or you could say pi times diameter, either way. All right, that's how you find circumference of the whole circle. Okay, so what we're going to do here is we're going to just take our 90 degrees, divide that by 360, and the circumference of the whole circle would be, my radius is 20, so my diameter is 40 times pi. Okay, and go ahead and multiply that out. Don't use the pi button, just leave it in terms of pi. You should get 10 pi feet. Okay, that's to Noah's position. That's to Noah's position. All right, now all the way to Elena's, it's going to be 90 plus 120 is 210 out of 360 times, same thing, 40 pi. So go ahead and multiply that out, and we need a calculator for that. I get 70 pi over 3 feet. Okay. So now you may know or you may not know, if your angle is in radians, you could also do your theta times your radius to get arc length if theta is in radians, okay? So what you could also do here, and I guess I'll come down here and just show you, the 90 degrees in radians, that's pi over 2 times your radius of 20. Check out what happens here. These cancel, and we get 10 pi, which is kind of what we had over here. Okay. Then the other one would be, let's see here. That would be 7 pi over 6 if I were to do 90 plus 120. That's 210 degrees, which is 7 pi over 6 times my radius of 20. And that ends up giving me the same thing, 70 pi over 3, which is what I had. But you might not know that formula. I'm guessing this one here you're probably more familiar with, okay? But either way. All right, question 2. The carousel makes one complete rotation every 10 seconds. At which times will Jada be in her starting position? So if I go back up here to my picture here, so she starts at 0, full circle, 10 seconds. Another circle, 10 seconds. Another circle, 10 seconds. So very obviously, Jada will start at time 0, and then every 10 seconds she'll be back where she started. It'll look like that. Now Noah is actually a quarter of a circle. So if this is 1/4 of a circle, 1/4 times 10 is 2.5. So Noah will cross his point at 2.5 seconds. So it's going to take 2.5 seconds to get here. And then a whole nother circle around there would be another 10. So it'd be like 12.5. And then another circle, 22.5, and so forth. Okay, so there's Noah's and there's Jada's times. All right. And the carousel ride lasts for 3.25 minutes. Where will Elena be when the ride ends? So here's the thing. 3 minutes and 25 seconds would look like that. It doesn't say 3 minutes and 25 seconds. It says 3.25 minutes. So if you took 3.25 times 60, that's going to tell you how many total seconds you go. So it ends up giving you 195 seconds. Okay, if that's confusing to you, you could think 3.25, 60 seconds in each minute. So we got 60, 60, 60, and then 0.25 of 60 is 15. Okay, a quarter of a minute would be on a clock, like 15 seconds. That gives you the 195. So let me go back up here to my picture. I'll come up here. I'm going to highlight. So Elena, so every 10 seconds she ends up right here. So she's going to go around 19 times basically, and then she'll end right back at E. But then she's got 5 more seconds to go. So she's going to actually end up right clear on the other side, right there. I'll call it E prime, Elena prime. So she will end directly across the circle. At E prime. Okay. And she will have gone around the circle 19 and a half times, basically, because every 10 seconds she does a full rotation or revolution. Okay, take a minute, pause the video, read this next situation. It's very similar. Jada begins the carousel ride at point J and Noah begins at point N. The radius is 20 feet and rotates in a counterclockwise direction, making one complete rotation every 10 seconds. Okay, so if this is my center, this point is 20, 0. This is 0, 20, and 20, 0, 0, negative 20. So those are the points right there at all those locations. So as this moves here, 0, 20, negative 20, 0, 0, negative 20, back there. Okay. So we have to write an equation describing the horizontal coordinate of Jada's location as a function of time. And we also need to sketch it. So I'm going to kind of do these two together. So as time goes on here, I'm going to label this 2.55, 7.5, 10. I think your book maybe goes by 5, so maybe mark in between every 5 seconds. And think about this here, not same thing as the last problem. 10 seconds all the way around, so to go this distance would be a quarter of 10, so it would be 2.5. So let's see here. Jada starts with the horizontal distance of 20. So at time 0, I'm going to start at 20. And then at 2.5, the horizontal distance, and I'm going to highlight the horizontal distances. So at 2.5, her horizontal distance is 0. At 5, her horizontal distance is negative 20. 7.5 back to 0. And then 10, she's right where she started. So your graph's going to look something like that. If I wanted to write a function, well, I'm going to say y equals, my amplitude's 20. Since I start up here at the top of my function, I'm going to use cosine. And then I got to figure out b. Midline is 0 because it goes through the y-axis, so it's always like a plus 0. I don't need to put that there. I'm going to erase it. So to figure out b, remember your formula, period equals 2 pi divided by b. We know our period is 10 because we do a full period at 10 right there. Okay, so I'll plug in 10 for p. And now I just got to solve and find b. So if I times each side by b, I get 10 times b equals 2 pi divided by 10. And I get b equals 2 pi over 10. If you want to reduce it to pi over 5, that's fine. So my function is going to be cosine of pi over 5 times, I'm going to use t for my variable, use x or theta, but I'm going to go with t. And there you go. Now, for number 2, we have to describe the vertical coordinate of Noah's location as a function of time. So here's what I'm going to do. I'm going to go up here. I'm going to just basically move my highlights to the vertical coordinate. And here's the thing. We're starting at a different spot. We're starting up at the top. We're starting right here. So this is your start. So at time 0, the vertical component is 20. So if I come down here, it's going to kind of be the same graph, actually. At time 0, he's up here at 20. Oops. At 2.5 seconds, he's going to be right here. And then 5 seconds, and then 7.5, and then back 10 seconds back there. So you kind of go like this. And you end up actually getting the same graph because you're looking at a different piece. You're looking at the vertical component, and then we've also changed our starting point. Okay, so same function because it's the same graph. I guess, what does the graph tell you about Noah's location during the carousel ride? I didn't answer that on the other question too. So we're going to say we're between negative 20 and 20 at all times. He repeats every 10 seconds. Okay, and that's going to be the same for up here as well. Okay. Okay. Synthesis here. The horizontal position of Lynn in feet relative to the center of a carousel is given by this function, where t is the number of seconds since the carousel started moving. What's the radius? So the radius is going to be equal to the amplitude. Okay, 20 I guess I should probably label that 20 feet, which is equal to the amplitude. Okay, amplitude is that number right in front. How long does it take to make one complete revolution? So again, we are looking for period. So period equals 2 pi over b. So my period is going to be 2 pi over, here's my b. B is the number in front of the variable. So 2 pi over 25. So my period equals 2 pi. It looks kind of funky, but when I just multiply by the reciprocal, those cancel and we get 25 seconds is the unit, I think. Okay. Where is Lynn on the carousel when the ride begins? So when they begin, that means that time is equal to 0. So I'm going to just take my function, plug in 0 for t. And when I do that, that's all gone. So my height is, or my horizontal distance, not height, cosine of pi over 4. You can type it into your calculator if you put it in radian mode, because that angle's in radians. You can do 20 times the cosine of pi over 4, which is going to give you 14.1 feet. Or you might remember that the cosine of pi over 4 on the unit circle is radical 2 over 2. So if I do that, I'm going to get 10 radical 2 feet. That's exact. If I type in 10 times the square root of 2, I'm going to get the same number. I'm going to get 14.1. Okay, this is better because it's exact, but either way would be fine. Okay. All right. Back to our learning target. I can represent a circular motion situation using a graph and an equation. All right, and then last thing, a little cool down here. Kieran is riding on a different carousel. Here's a view of the carousel from above. This carousel makes one complete revolution in a counterclockwise direction every 40 seconds. Find an equation that represents Kieran's horizontal position, h in feet relative to the center. 2 seconds till it starts moving. So think about this here. Here's my center, horizontal position, negative 15, 0. Down here at the bottom, we're at 0, negative 15, 0, 15. I'm sorry, that's 15, 0, heading backwards. And 0, 15 up here. So on my graph, I'm going to start down here at negative 15. And then it takes me 40 seconds to go all the way around. So this distance here is going to be 10 seconds. So back to 0. All right, I'm looking at the horizontals. 20 seconds up at 15. 30 back to 0. And then 40, we get back to the starting point down here at negative 15. So if I were to write an equation for this, I'm going to use my cosine function, but it's going to be negative because I start down at the bottom. Amplitude is 15. And then I don't need to add any numbers on. My midline still 0. But I do need to find b. So remember, period is 2 pi over b. So 40 equals 2 pi over b times each side by b. So b equals 2 pi, whoops, over 40. So you could call it pi over 20, or you could just leave it as 2 pi over 40. I think our book leaves it as 2 pi over 40. Okay, you can leave it like that. Or I would probably reduce it that. And there you go. All right.